megahertz. The other signal to noise ratio that we refer to is the EB on N0 or ES on N0, bit energy to noise spectral density ratio or signal energy to noise spectral density ratio. That will be clearly defined. So in the previous question, in part A, you can say we define SNR as EB on N0. So clearly mentioned what the SNR we are referring to. In this problem, it's signal to noise power ratio. So that's PS on PN, all right? 4 dB. So bandwidth of 5 megahertz and a data rate of 2 megabits per second. So we need to calculate the bit error probability for different modulation techniques under for this particular channel parameters or link budget parameters. So the main KPI for calculating bit error probability is EB on N0, right? EB on N0. So we've been given PS on PN, the power signal to noise power ratio, and then we need to convert that into EB on N0 using this R and P, and then we use existing equations or expressions for bit error probability to solve this problem. Okay, so let's see how it goes. Okay, so that's week 5, Q2. Signal to noise ratio, gamma is 4 dB. Bandwidth is 5 megahertz. RB data rate is 2 megabits per second. Okay, so from this EB on N0, EB on N0 in dB, the relationship between EB on N0 and the signal to noise power ratio is this. Right, so RB. So EB on N0 is signal to noise ratio plus B on RB of log base 10. So in other words, the real relationship of in linear units is the signal to noise power ratio times bandwidth on Rs. So this is easy to remember because if you multiply power by bit duration, one on RB is the bit duration TB, right? So 1 on RB is TB. So if you multiply power by time, you get the energy, and if you divide the noise power by the bandwidth, you get the noise power spectral density, right? So that's an easy thing to remember. So I can just write that here. So EB is PS times TB, where TB is 1 on RB, right? And then N0 is your noise power divided by the bandwidth. So if you substitute values from here, we have 4 dB plus 10 log base 10 of 5 on 2, and that will give us 7.98 dB, or in linear values it's 6.28. Okay. So part A, so once we have the EB on N0 value, in week 5 lecture slides, you will find the different bit range expressions for the different modulation techniques. Binary frequency shift keying, binary phase shift keying, quaternary phase shift keying, M-ary phase shift keying, MPSK. So that's mth order, rectangular M1, and also if we go further down, we have the direct sequence spread spectrum as well. All right. So let's go back to the shorthand. So part A is to calculate using QPSK. The beta error probability for QPSK is Q of square root of 2 gamma. So let me define gamma. This as gamma here. All right. Okay. So this is gamma and this is gamma here. And then we just need a substitute value that will become Q of 3.54, and if you use, so I'll do one of the Q values again here. So Q of 3.54 and 3.54 is that here, because it's 5.4, we want get 5.6 result over 3.5, and it's 2.32 into 10 to the minus 4. Right, 2.32 into 10 to the minus 4. So I'll do that again. Q of 3.54, right? So square root of 2 gamma. When you substitute gamma here, you'll get 3.54. And then 3.54 on the Q table. Q of 3.5 is 2.3 into 10 to the minus 4. So that's 2.3 into 10 to the minus 4. Right. So it's a straightforward calculation for beta error probability. So remember, this gamma here in this argument is linear value, right? So this is this gamma. Because in the Q function we don't use AB values, we use the linear values. All right. Then part B is for binary FSK modulation. So same process for binary FSK modulation, and your beta error probability there would be Q of square root of gamma. That's the definition, and that square root of gamma becomes 2.5 once you substitute. And when you use the Q value, Q table, you get 6.2 to 10 to the minus 3. Okay. So these are pretty straightforward things. I'm just showing how to do the calculations, right? Part C is for M-ary QAM or M-QAM, where M stands for the order of the modulation. So M-QAM, where M is equals to 16. So that's part C. 16 order. So it transmits 16 symbols, right? So the beta error probability expression for this is four of square root of M minus 1 on square root of M log base 2 of M Q of whole thing 3 gamma base 2 of m divided by m minus 1. Right. So here in this equation, m is 16 and gamma is 6.228, and these are the only two parameters that you need to compute this expression, and you should be able to do that. So I'll just provide the answer there. It will be 1.04 into 10 to the minus 2. So an important thing that you need to understand here is for the same link budget, for the same system, how different modulation techniques perform different, right? So QPSK, 2 bits per symbol, you get a bit error probability of 10 to the minus 4. Binary phase shift keying, so sorry guys, I think you can just be quiet a bit, thanks. Binary frequency shift keying is 6.2 into 10 to the minus 3. Now FSK is known to be power efficient, not necessarily providing higher, better bit error probability. So you can see between the answers of A and B. And C, when you increase the modulation order, that means that for the same energy in the IQ space, for the same energy, you're packing in more and more symbols. So when you pack in more and more symbols, 16 symbols in this case, for the same energy circle in the IQ diagram, that means that differentiating between the symbols becomes a bit harder, especially with noise. So in that case, your bit error probability will increase compared to lower value of n. Okay. All right. So part D is for direct sequence spread spectrum, and the direct sequence spread spectrum. Question here. Direct sequence spread spectrum is a bit different, or completely different modulation technique to the other modulation techniques in parts A, B, and C. So for DSSS, we have something called the processing gain 200, and the total number of users is 50 in this case, right? So the direct sequence spread spectrum, it basically provides unique codes or sequences to different users. All right. Therefore, it depends how many users are there to differentiate between users. So if you have 2 users, the direct sequence spread spectrum will perform better than having 100 users, because you got to differentiate between the users, and there's a self-interference factor in there. All right. So there's an expression for direct sequence spread spectrum as well. So part D, just need to use that expression for PB, which is the Q function again of 1 on square root of K minus 1 on 3n plus 1 on 2 gamma. Right? So the direct sequence spread spectrum also performs for 2 users, case for infinite users here, right? When n is infinity, this becomes 0, right? And then it becomes a only 2 gamma comes into the picture, only the signal to noise ratio comes into the picture when you have large number of users. So that's something that you need to keep an eye on. So K is given as the processing gain is given as 200, and the number of users is given as 50. So I think K is given as 200, and the number of users is given as 50, and then you just need to solve for this, right? So we're going to do this, and then the solutions are there in the tutorial. All right. So the same thing for part E as well, for different parametric values. Processing gain of 100 and 100 users. All right. Any questions in solving this? Pretty straightforward. And then it's really important that you all again practice these, so that you don't have any doubts when you try to do this during the test. How do I calculate Q values and so on? So for example, if your signal to noise ratio calculation is wrong, you will probably find a argument for Q value that is outside this table, right? So make sure you just go back and recalculate your signal to noise ratio in that case, right? So did you have a question? Sorry. Did you have a question?
So, do we need to? Are you giving this one, right?
Sorry.
In the test, are you giving this one, right?
It's an open book test.
Okay.
So if any other questions? All right. So let's move on to the third question.
So just clarifying that the gamma there is linear.
Linear, right? Yeah. Correct. All right, how about this? I'm going to give you all a few minutes to try Q3 part A. I would like you all to genuinely try this out, so that that helps you with your final test. So there's a BPSK transmission scheme. I hope you have access to the lecture notes, but in the previous. The BPSK bit error probability is the same as the bit error probability for QPSK as well in Q2 part A. So you can use that. What is the bit error rate for this transmission for the gamma of 8 dB? Sure you don't use the dB value for the gamma. Change the linear value.
question to
EPS case.
sorry.
Diffusion হলো যে E equal to Q into root over 2 r. This is it.
Anybody got an answer?
But এটা লাগবে এখানে। So we do need the
Q table?
yeah.
All right, there you go. What's the answer? The same answer is Q2A, right? The same problem as Q2A. Well, the solution turns out to be the same because it's different modulation technique. However, the same bit error probability expression for the same signal energy to noise density ratio. Sorry?
It's only 7.98 dB. It's 8.
Yeah, yeah, close enough. Yeah. And when you look at the Q table, it just rounds it up anyway, right? Anybody has questions on this? Everyone be able to do this?
Can you see a question? Can
Yeah.
you see the question?
You want to see the question? EB on N0 of 8 dB. All right, so let's give it a try. Let's give a try of part B as well. So, if this transmission is now a wireless transmission in a Rayleigh fading channel, right? So hints are given, meaning that a Rayleigh fading channel means either you know the average bit error probability in a Rayleigh fading channel or the outage probability, right? So these are something that you need to be very familiar with, all right? So for an Rayleigh fading channel, we know how to calculate the outage probability, right? We need the average signal to noise ratio and the threshold signal to noise ratio that will give us an outage probability. So if this is a transmission in a relay fading channel with a mean received signal to noise ratio of 30 dB. So the mean received signal to noise ratio is 30 dB given. Okay, so that's a received SNR or EB on N0. What is the outage probability to have the same bit error rate? So what is the outage probability to have the same bit error rate? I'm not going to give a hint after that. So the outage probability depends on two parameters: the mean signal to noise ratio and the threshold signal to noise ratio. And for the relay fading channel, you can refer to week 4 slides if you want for the outage probability in relay fading channel. Let's see if you can find the outage for this transmission. Yep.
Just a second. Is it binary B scheme? Is that the same as this one?
No,
It's different, right?
that's different. Yeah.
So this one is accumulate plus A, right?
BPSK and QPSK have got same bit error probability expressions, but they are different modulation techniques.
Oh, just taking
Different.
But the thing is, you know, this one's ADB, right?
Mhm.
I want to change to DB is 10 power 8. This is about 10,000 right?
What? 8 dB is equal to divide by 10, so it's 10 to the power of 0.8.
Oh, but 2 linear, right?
Yeah,
2 linear is 10 power something.
10 to the power of
Of 0.8, yeah?
yeah 0.8. Yeah.
Yeah. Okay. Mhm.
So the outage probability expression is E out is 1 minus exponential minus gamma 0 on gamma bar. So this is your gamma bar.
So all has to be linear, right? All the
Gamma in this model, gamma is linear. Any solutions? Any answers? How much? How much? 2 answers? 2. Yeah, it's a probability. All right, let me come and have a look.
Oh, someone can get that. 8 or better. Gamma bar will be 30.
Any answers? I got one. 6.3 into 10 to the minus 3.
Six point two eight into 10 to the power minus 3.
2.8, 6.3. Accurate enough. That's the correct answer. So this is how you need to push yourself when you're learning for the test. You got to know what are the major results in the in terms of expressions and equations, outage probability, probability of bit error. So those major results, I think you need to understand where they are. All right, so what's the problem here in part B? It's a Rayleigh fading channel, so this is the outage probability expression for a Rayleigh fading channel. Gamma 0 and gamma bar, and these are linear values. Gamma 0 is the threshold signal to noise ratio level, right? So in order to achieve gamma 0 in a gamma bar link, what is the outage? That's what it is, right? So I'll repeat that again. In a link that provides gamma bar, which is that, and to achieve gamma 0 in a gamma bar link, what is the outage? So your gamma 0 is the required gamma 0 for the bit error probability, right? So if you have gamma 0, then you will have that bit error probability, and to achieve this gamma 0 in a gamma bar environment, what is the outage, right? So the outage P0 is 6.3 into 10 to the minus 3, which is really good. Because so in other words, it's just common sense, right? You need 8 dB only to achieve the bit error probability. But on average, you're getting 30 dB in the random environment. So there's a very high chance that you will get at least 8 dB, and the chance is 1 minus this P0 value, right? That's how you understand the problem. Okay, so I'll just write the answer here itself. 1 minus exponential minus 8 dB is what? 6.3 on 1000. That's 6.3 into 10 to the minus 3. All right. So now this is a challenging part as well. Can you try and attempt this? So for a call duration of 100 seconds, so it's a call duration of 100 seconds, what is the amount of time the bit error rate of the call would be less than or better than the bit error rate in part A? So in order to have at least a bit error rate of whatever that part is, how much in a 100-second call period, over how long would we have a bit error rate that is at least what was part A? So you've got to relate that to the outage probability, or relate to the duration. Okay, so the outage probability in part B is the probability that the signal to noise ratio is going to fall below gamma 0, right? So when that outage happens, your bit error probability is going to be worse than part A, what you calculate in part A of 8 dB, because your SNR will fall below 8 dB. So in a 100-second call, what is the duration of that call? Your bit error probability will be greater than what was achieved in part A, meaning that you just need to multiply 100 seconds by 1 minus the outage. So 1 minus the outage is the time that your bit error probability will always be less, right? So your bit error rate of the call would be less than the bit error rate in part A. In other words, your gamma would be greater than gamma 0 during this time. That is the availability, 1 minus the outage. 1 minus the outage is the availability. So if you multiply 100 seconds by 1 minus P0, then that's the amount of duration you will have the call quality as per the design. All right. So let me just put that part C solution there rather than rewriting it. So
Yeah.
the call duration is 100 seconds, right? The duration of the call where the bit error rate is expected to be less than PB from part A is the same where the SNR is greater than gamma 0. So SNR greater than gamma 0 is 1 minus the outage, right? That's the probability of 1 minus the outage probability. And therefore, the duration of the call is 1 minus P0 times the call duration, 99.37 seconds, right? So 99.37 seconds out of a 100-second call, you're going to have a bit error probability of good quality as per this, right? So this is how you should relate what we learned in this course, right? You've got to relate the design aspects and the calculations with real world systems. Okay, so I think that concludes week 5 tutorial problems, and I would like to start off with week 7 because week 6 we have a mid semester, so